Okay, today's video is all about concentration. Now, first of all, some units. Most of our volumetric glassware, that's glassware for measuring volumes, is measured in centimetres cubed, which equals a milliliter, which is what you might use at home. What we need to be working with, if we're working with moles, is actually a decimetre cubed, which handily is the same as a litre. So there are 1,000 centimetres cubed in 1 decimetre cubed. These are what we call SI units, and they are the standard chemistry units. So what do we need for concentration? Well, concentration is the amount of solute, that's something that's dissolved, in grams, dissolved in 1 decimetre cubed of that solution, is the standard way of measuring concentration. So, that's one way anyway. We can also measure it in moles. 2 ways of doing it. So 50 grams in 1 decimetre cubed is going to give us 50 grams per decimetre cubed. Likewise, 10 moles in 1 decimetre cubed is 10 moles per decimetre cubed. This is what you tend to see more often in chemistry, moles per decimetre cubed. Now, the first thing we need to think about is dilutions. Let's say we've got our beaker, and into that beaker we've put 100 centimetres cubed, and it's got a concentration of 100. Let's start with grams per decimetre cubed. What do we need to do? Well, in order to halve that concentration, we want to get to 50. Let's say. If we're going to halve it, we can't just take molecules out of there. It's too difficult. The only thing we can do is go, well, this is in a unit volume. We've got 100 centimetres cubed. Let's take our beaker and fill it full up to 200 centimetres cubed. That will give us 50 grams per decimetre cubed, because we've doubled the volume but kept the number of molecules the same. So let's represent that 100 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've still only got 10 spots, but they're in twice as much volume. So if I were to take half of that volume, there'd be 5 in each, half the concentration. So that's a simple dilution, adding liquid. That's all you can really do with these dilutions. In fact, you can't halve the number of molecules. If you're making something more concentrated, you could add some more of the stuff. But if we're diluting, we can only add more liquid. So, what we need to think about is how we actually do these dilutions carefully. If I want to make a solution that's 10 times less diluted and I've got 1 centimetre cubed. I want to divide the concentration by 10. I need to end up with 10 centimetres cubed, don't I? I want to divide that concentration by 10. But I've already got 1 centimetre cubed, so I need to add 9 centimetres cubed to give me a total of 10 centimetres cubed. You're always looking at the total volume. So you're taking 1 centimetre cubed, you're going to dilute it up to 10, but in order to do that you already started with 1 centimetre cubed. You need to add another 9, not another 10. Now here's an equation that we can use. Concentration is moles divided by volume. I quite often abbreviate this as concentration is M over V. Concentration is moles over volume. So imagine we've got 500 centimetres cubed of a 0.1 molar, which is moles per decimetre cubed. Notice I've dropped the ES. It's perfectly acceptable. Chemists are lazy. Well, concentration is moles over volume. But we know the concentration, we know the volume, so we're looking for the moles. So moles is concentration times volume. Straightforward little rearrangement there. M is C times V. Concentration is 0.1. This is in centimetres cubed though. We need it in decimetres cubed. Which means that we've got 0.05 moles of whatever it is we were looking at. We've just rearranged the formula, made sure we've got the units correct, and worked it out. Sort of thing they might ask you to work with. Bit of dilution, bit of concentrations. Second half of this video is about some less numeracy based content. First thing, guideline daily allowances. So these are going to depend if you're a man or a woman, pregnant, child, all sorts of things. They are the guideline amounts that generally the government has been suggested. And the reason this ties in to what we've just been talking about is concentration. I mean, imagine you've got a nice bottle of squash. Lovely bottle. Nice neon orange squash. It'll have a label on it telling you how much sugar there is in there. Now if you make up a glass of squash, and you put in the amount suggested, the correct concentration, that's going to give you a glass of squash that goes with the label on the bottle. But this one is going to have much more sugar in, much more of the other nutrients as well, I suppose, but mostly squash contains sugar. So you're not going to get the correct nutrients. The other option that we might talk about are things like baby powder. If you don't like dilute baby milk powder enough, it's going to be too thick. If you dilute it too much, the baby isn't getting the correct nutrients. So understanding how these concentrations work is quite important to know that you've got to get them right. Now, food labels. One thing it's worth knowing about are these colour codings. The government has mandated that different companies should have a traffic light labelling system. You should see this on packaging. You can go and have a look. Green means it's got a low value relative to your guideline daily allowance. Orange is it's got medium, and red if it's got a high, usually approaching your guideline daily allowance. If you're eating things with lots of reds in, think very carefully about what you're eating. Maybe reduce your consumption of those. But they vary a lot. Sometimes they're printed on the boxes, sometimes they've got the traffic lights on the front of the box, all sorts of things like that. The important thing for you is you might get asked in an exam to work out some things. One thing you might be asked to work out is to convert the amount of sodium into salt, because usually on a food label it won't say salt, it will say sodium, because you can get sodium ions from lots of different places. Well, sodium chloride is salt, it's NaCl, and its formula mass is 58.5 grams per mole. Sodium is 23 grams per mole, which means that for every 23 grams of sodium, you've got 58.5 grams equivalent of salt. So what we can just do, 2.5 times sodium mass equals the salt mass. Let's call it the salt mass equivalent. If it were all salt, it would be 2.5 times the amount of sodium. So it's worth looking at that and making sure you understand how to do that. Simple little shortcut there to do that. Now, the reason they do this is because prepared foods might contain things like sodium nitrate in preserved meat or other sources of sodium. And it's the sodium that's important, so we think about that. Now, don't worry about the dilutions too much. All you need to be able to do for the dilutions is divide by 10. We've talked about concentration of solutions, we've talked about decimeters and decimeters cubed, 1,000 centimeters cubed to the decimeter, we've talked about dilutions, we've talked about why it's important. The other thing you need to know, medicines need to be diluted to avoid giving overdoses if you're having liquid medicines. We've talked about guideline daily allowances. We've talked about concentration calculations and conversions of centimeters cubed to decimeters cubed. We've talked about dilutions and interpreting packaging and salt and sodium conversion. Excellent.